This is more about circles and things that happen in them. We recall that we dealt with intersecting lines that intercepted or subtended arcs, that we found that the arcs averaged to the central angle no matter where it was located. That was the arcs. Today we're going to talk about the segments that are inside of the circle. In this case, chords that intersect somewhere inside the circle. So if we start with them like this, we'll notice that they're all radii. So all the sections from the circle to the center are radii. We could, if we wanted to, but why? But for the purpose of argument, we'll make a proportion. The left top to the left bottom and the right top to the right bottom. When we make that proportion, it'll be 1 equals 1. But it is proportionate. Look what happens if we move along the diameter to the left. Now we've got 2 shorter ones on the left and 2 longer ones on the right. But say it still looks proportionate. The circle took away and the circle gave. The circle took away and the circle gave. It still looks proportional. That is about half of that, and the left bottom is about half of the right bottom. These two still being equal, approximate, and these two still being equal. Again, because the circle is, round. So I would still have a proportion. Say if this was 2 units, it would be 2 is to 2 as 4 is to 4. It would still be an equal proportion. Anywhere along we come in here, if it gets little bitty tiny segments of chords here and big segments of chords here, these are still equal. The short ones and the long ones are still equal. It's still proportionate. It's still 1 equals 1. Why? Because the circle taketh away and the circle giveth. What if we come up this way? Notice that now, if we're looking at it from this perspective, which is just sideways from the other one, we have a short and a long and a short and a long. But since I've stayed on this diagonal, the 2 shorts are still equal and the 2 longs are still equal. So like if this long is twice the short, then this long is twice the short, and they're equal to each other. This would be like 1 is to 2 is 1 is to 2. It's still an equal proportion. Why? Because the circle is round, it taketh and it giveth at the same rate. What if I make it crooked? Well, you look at it and it still looks proportional. If this one, upper right, is twice the upper left, and the lower left is twice the lower right is twice the lower left, which it appears to still be holding that relationship, and actually it really does. What we can see is that we can still make a proportion. Say this is 2 units to 3, and this is 4 to 6. So 2 is to 3 is 4 is to 6. That's a valid proportion. If you look around, as we move it around the circle, you can tell that that's always going to happen. As we just play with it and think of a proportion with the left ones and the right ones, it still works out just fine wherever we put it. So what we'd have if we do that then is, let's look at this diagram first. And the diagram well, let's make a proportion of it. Let's make one. A is to D, this portion of red to that portion of green. Like I just said, top left, top right. How would that work out? What I would do, I would put AE, which is the top left, is to DE, bottom left, as CE, top right, is to BE, bottom right. It would still be proportional. Again, the circle's round. It takes care of that. We'd have a proportion that looks like this. And as you work these problems, you can use them as a proportion, and you'll recall that our properties of proportions allow us to write multiple ways to do the proportion. I've chosen this particular way because it works out to be particularly handy in when we're using these chords. And our theorem that we're going to have does not give it in the proportion, but rather as a solved proportion. So what we'd have here then is we would do our cross products. AE times BE equals CE times DE. Okay, what's the advantage of this one? Well, it's handy to write it this way because notice that AE and BE are both on the red chord, and DE and CE are both on the blue chord. So that makes it easy because you can just say in the same chord, piece times piece equals the other same chord, piece times piece. So piece of red times piece of red, same chord, equals piece of blue times piece of blue in the same chord. That makes it handy to use. If you find a time that you want to use a proportion in a different way, that's just fine. But here is our theorem stated out that has it. So you'll want to write this in your cipher, please. I'm sorry today, they're kind of long. I usually abbreviate them the best I can, but I wasn't having much luck in abbreviating these. Let's look at some problems. Problem number 3 there. Find the value of x. Well, this isn't one of the harder ones. Doing it according to the theorem, that would be 10 times 6, which is 60, equals 12 times x, or solve that and x equals 5. If you wanted to do it proportionally, you could do 10 over x equals 12 over 6. Twice as much, that still gives you n equals 5. There's this problem and 2 others. Please do number 5 anyway. It would be good for you to do number 4 for some practice, but please do number 5. Here are the answers to all 3 of them. And here's how I worked out problem number 5. A reminder, whenever you have a quadratic, you're going to have 2 answers. Sometimes they might be the same, but 2 answers. Don't automatically disclose. First off, you recall you can't have a negative side length, a negative length, and so you will need to check into your original diagram. Substitute both values into the variables in the original diagram to determine if it resulted in a negative length. It does not always, and it's not always the one that where the variable was negative. You have to check them both. Sometimes they're both good, which would be usually a different shaped diagram, but you remember that we're more concerned with the calculations than with what the diagram actually looks like, that calculations will supersede what the diagram looks like. Another one. Instead of 2 chords, now we're looking at 2 secants. So the 2 secants would be, they have chords in them. And when we just talked about the chord portion of it, we could work within them inside the circle. Now I'm extending it out to an external point that's common to the 2 secant segments. And I'm wondering if I can find some handy-dandy relationship with these outside things and the inside things. That other one we got was really easy. Multiply the 2 segments times equals the 2 segments. That was no sweat. So let's look and see if we can work out something that might help us on this one. Okay, well, the first thing I'm looking at this and I think, I see an angle, I see some lines. I'm thinking triangles. Let's see if I can make some triangles. So I'll start here. That looks like a triangle. I'm looking at the triangle BEC. So that's going to be the one that comes out here. And I can make one going down the other direction. pretty much the same, but upside down. Same idea. I'll draw a segment, a chord from A to D. And now I have another triangle, the lower one here, and it goes here with the blue ink. Two triangles. Well, I'm looking at those, and if they were congruent or similar, I could just have a good time, corresponding parts and all that stuff. First off, all we've got is angles. We're not giving any sine lengths, so these are not going to be congruent. You'll recall, for triangles to be congruent, you're going to have at least one measurement of a length, and we don't have that. So our only possibility is similarity. Let's see if that'll work. You recall angle, angle, angle will get it for us, but angle, angle is really all we need. Well, one angle right here is really easy. The pink triangle and the blue triangle share the angle at E, so that's reflexive property. It's in both triangles, so that's easy. How about another one? Let me think. Seems like I remember something about angles that open to the same chord are congruent to each other. The angle in B is inscribed. The angle at D is inscribed in the circle, and they both open to the chord AC. Therefore, angle B is equal to angle D. We've got angle, angle. We're good. They're similar. If we wanted to go for overkill, we could get the angle at A, blue, and C, pink, pretty easily, because A and C, the inscribed angles at A and C, both open to the arc BD. That gives us not the angle that we want. We want the one inside the blue. That gives us the angle at A that's not. But it is supplementary, and the angle that's not inside at C is also supplementary to the angle that we want. So we have angles that are supplementary to angles that are congruent or congruent to each other. So we also know that these are congruent overkill. So now that we've done that, we can make us a proportion because we recall that corresponding sides of similar triangles are proportionate. So I was interested in this outside stuff to see if I could get something easy for the outside stuff. So I'm going to use sides of triangles that relate to what's on the outside. I'm going to start with the blue triangle. And let's see, blue. So for the blue triangle, that'll be side AE is the secant segment on the outside, A to E, and then the long one in the blue triangle is segment DE. So that's for the blue triangle. In the pink triangle, the corresponding sides are outside the circle is CE, and the long one opposite is BE. Because corresponding parts of similar triangles are proportionate, we can write this proportion. And again, for reasons you'll see in just a moment, it'd be really handy to work this as a solved proportion instead of a proportion. So I'll do my cross multiply. AE times BE is equal to CE times DE. We have a theorem about that, and here it is. Segments of secants. Notice once you see it now like this, you can kind of tell that it's going to be handy because AE and BE are both on the same secant segment. CE and DE are both parts of the same secant segment. So what we have here is outside times whole equals outside times whole. The external segment of the secant times the whole secant segment equals the external times the whole. Let's investigate here. Copy this in your cipher. Let's investigate here what else this is. It's starting to look kind of familiar here. This formulation here, it came from a proportion, right? Oh, no, wait. I'm sorry. Back to this. Let's go to the next step. I'm sorry. So the next step, we're going to look at this and find out our next step. So if I have my shape and I have a line, I'm going to play around with it a little bit. Okay. My line segment, my secant segment, BE. There's disappeared. Well, let's look at this. External times whole equals external times whole. All right. Well, what if I do this? Is it still going to work? I move A up here and B up to here. I've still got external times the whole equals the same down there. It's still going to work. And again here, if I move A up here, B over here, well, that's still going to work. I can still draw my triangles down and up, get similar triangles, write my proportion, and it'll still work. That external times whole equals external times whole. Okay, what if I move it really close? There's A to the circle. There's A, there's B. I can still draw my triangles. It's still going to work. What if I put it at the tangent position? So now instead of having it at BA, which we just showed, I have it up here. Well, B and A are now both right there. That is the external, and it is the whole. It's both. So what do we have? Does it still work? Could I still draw the triangles? Indeed, I could. So what we have here is that E to BA squared. E to BA times E to BA equals external times total. And here's that. I just named it from the A. You could have named it the B or the A, obviously. I just picked A. So what we have here is that the tangent segment is equal to the secant segment external times whole. Write that one down in your cipher, please. And let's notice another thing about this, which I was about to say too early. That is, where did this come from? Let's see, this was AE times AE. That's what squared means, but you already knew that. So then what I have here, that looks like that could be proportionalized. It looks like it came from a proportion. And indeed I can. What I can do is I can divide and transform this into CE over AE equals AE over DE. This should look familiar. Figure out what it is. Again, this is multiplied AD times, okay. Figure out what it is. Well, look here. This is what should look familiar. The means are the same thing. This is the geometric mean. So what we have with this theorem is that the tangent from the same external point is the geometric mean of the external sequence, secant, and the whole secant segment. It's the geometric mean. Okay, a few problems about this. Let's look here at some of them. If you would, do problem number 6 and problem number 8. Here's 6, so you can see it. And here's the answer to problem number 6. How it's worked out. Do problem number 8. There you go. And here's how to work out problem number 8. It's kind of a mess. It's a quadratic, but it's doable. You're all proud graduates of Algebra 1. You can do it. Then problem 11 looks like it's about as bad, but it really isn't. So work problem 11. There it is. And here is the solution to problem 11. See, that one wimped out. It was pretty easy. The two x squareds cancel, so it doesn't really turn out to be a quadratic. Okay, go ahead and work several of these to make sure that you've got it good under your belt and you know what you're doing. I'll put the answers up, so you should freeze it right now. Here are the answers to those problems. Here's a few more just for the fun of it. Help you get good at it. And here are the answers to them. Okay, this is kind of a fun problem. Work this one out. The circular stone mound in Ireland is called Newgrange. Has a diameter of 250 feet. A passage has a diameter a passage is 62 feet long and leads towards the center of the mound. Find the perpendicular distance from x, the perpendicular distance x from the end of the passage to either side of the mound. Give that a go, pause it, and I'll put the answer up. Here's the answer. Now, if you want a really interesting one, oops, there we go. Give this a try. You'll pause it. Then I'll put the answer up. Here it is, 25 times the square root of 29 over 29. Now, a small housekeeping matter. You'll need these two handouts from class, and this is how you're to mark them. Please make sure that you color them in this fashion to help your eye catch what you're supposed to do when you work these types of problems. There are 6 handouts for your glossary. Paste off 6 in the glossary and highlight these only in this fashion. And here endeth the lesson.